Hello everyone. Today I'll introduce the security features of Realtek's BLE SoC series. The outline for this security topic includes Introduction, Overview of security features in BLE SoC series, Security IP solution, Security scheme, Emerging trends in security technology. We are focusing on the crucial role of security in protecting valuable assets from a variety of threats. In any organization, understanding and safeguarding these assets is essential to maintaining trust and ensuring operational success. Our assets come in many forms, ranging from cryptographic keys and sensitive data to proprietary images and software. It is our responsibility to implement robust measures to protect each of these assets. First, let's answer the question of what aspects of the asset do we want to protect? 1. Confidentiality. Our primary goal is to ensure that information is accessible only to authorized entities. This involves implementing encryption and access control systems to prevent unauthorized access. 2. Integrity. We must guarantee the accuracy and reliability of our information. This means protecting data from unauthorized alterations and ensuring that it remains trustworthy and unbroken. 3. Authenticity. It is also crucial to verify the genuineness of our information and its sources. By doing so, we can prevent the use of fake assets and maintain the credibility of our systems. Then, let's take a look at the common threats to assets. 1. Software attacks. These are vulnerabilities that attackers can exploit through software applications. For example, Stack Overflow attack. It is essential to regularly update software, conduct vulnerability assessments, and apply security patches to mitigate these threats. 2. Basic hardware attacks. These are physical breaches requiring minimal technical expertise or tools. Measures such as basic tamper detection and controlled physical access are vital to prevent these threats. 3. Advanced hardware attacks. These attacks involve sophisticated physical intrusions using specialized knowledge and equipment. Implementing comprehensive security methods, such as side-channel leakage protection and tamper detection that detect an attack in progress and take appropriate actions. This table shows the different security features of Realtek's BLE SoC series. The SoC series includes C, D, E, G, and H. These security features include 3 parts: Security IP, Security scheme, ARM PSA certified. These 3 parts will be explained in detail in the following slides. Notably, the G-series SoCs feature high-level security capabilities and have obtained ARM PSA Level 2 certification. In the following sections, the focus will primarily be on the G-series SoCs. Okay, let's begin with the security IP solutions. AES, or Advanced Encryption Standard, is an essential encryption standard used globally. It ensures data confidentiality and integrity through symmetric key encryption. AES supports 2 types of key length, 128 bits and 256 bits. AES supports several modes to enhance its flexibility and security. ECB, Electronic Codebook Simplest Mode but not recommended for large data due to predictable patterns. CBC, Cipher block chaining provides better security by incorporating an initialization vector. CFB, Cipher feedback, and OFB, output feedback stream modes that convert block encryption to stream encryption. CTR, counter mode turns a block cipher into a stream cipher and is useful for parallel encryption. CMAC, Cipher-based message authentication code provides data authenticity and integrity. AES supports key management, which allows storage of up to 4 keys, each 128 bits long. The keys are write-only, enhancing security by preventing readback. Users must select an appropriate key prior to encryption or decryption tasks. AES supports DMA, enabling efficient data transfer directly between memory and the encryption engine without CPU involvement. Hash functions are algorithms designed to take an input of any size and produce a fixed size output, known as a hash digest. The output appears random and is used for data integrity and authentication. MD5 was one of the first algorithms to gain widespread approval, but in recent years, it has been compromised due to vulnerabilities to collision attacks, so most experts consider it unsafe. Algorithms in the SHA family are considered slightly more secure. Compared to SHA-2, SHA-3 offers a different structural approach and is designed to complement rather than replace SHA-2. In the current Realtek BLE SoCs, SHA-256 is the most commonly used. TRNG, or True Random Number Generator, is a device or algorithm that generates random numbers from a physical process, rather than a deterministic algorithm. The simple working principle of a TRNG can be described in 3 stages: 1. Entropy source activation, 2. Entropy sampling, 3. Random output. For the TRNG in Realtek's BLE SoCs, thermal noise is used as the entropy source. By using the generated slow-speed clock to sample a high-frequency clock, the sampled data needs to be post-processed to ensure that the random values meet statistical standards. The TRNG has passed the NIST SP800-22 test suite. Regarding the comparison between TRNG and PRNG, a PRNG, pseudo-random number generator, generates sequences using deterministic algorithms and initial seeds, whereas a TRNG provides higher unpredictability and security. However, TRNGs are typically slower than PRNGs due to their reliance on physical processes. Public key engine, also known as asymmetric cryptography, is a cryptographic algorithm that operates using 2 distinct keys, a public key and a private key. Main functions of PKE include encryption and digital signature. For encryption scenario, public key is used to encrypt, and private key is used to decrypt. For digital signature, private key is used to sign digital messages, and public key is used to verify these signatures. The key features of RSA are capable of supporting key sizes up to 3072 bits. Facilitates signing and verifying digital signatures. Supports encryption and decryption processes. The key features of ECC are supports key sizes up to 512 bits. Facilitates ECDH key exchange. Generates ECDSA key pairs. Supports ECDSA signing and verifying. Public key engine is essential to secure communications, offering strong encryption and digital signature capabilities, with RSA and ECC being leading algorithms. These features enhance data privacy and authenticity across digital platforms. Protection of image contents is a crucial requirement for SoCs. The image is encrypted before being downloaded into the device, and while the IC runs, flash on-the-fly decryption is used to decrypt the image. Consequently, it functions as a hardware security module situated above the SPI controller. When the processor fetches instructions from the SPI flash, the decryption IP reads data aligned with the cache line size and decrypts them before returning them to the processor. The key features of this IP include support for AES-CTR and GCM decryption modes, support for up to 8 regions, with each region using a different decryption mode and key. Each region must be 4 kilobytes aligned. The cache line buffer size is 32 bytes. ARM TrustZone is a crucial hardware-based security technology embedded in ARM processors. TrustZone is designed to address the ever-growing need for robust security solutions in modern computing environments, especially for devices handling sensitive operations and data. ARM TrustZone creates a secure environment, allowing them to manage sensitive operations separate from regular tasks. Essentially, it provides a dual-world processing environment, secure world and normal world. Secure World is dedicated to handling sensitive data and operations. It's protected and isolated from the rest of the system to prevent unauthorized access. Normal World is where regular, non-sensitive tasks and applications are managed, ensuring that they do not interfere with the Secure World operations. Trust Zone security is fundamentally built on partitioning, which includes CPU, memory, and peripherals. CPU partitioning. Trust Zone enhances CPU design with separate stack pointer registers and stack limit registers for secure and non-secure operations. For instance, MSP_S and MSP_NS handle secure and non-secure main stack pointers, respectively. Similar partitioning exists for the process stack pointers and stack limit registers. A separate vector table is maintained for secure and non-secure operations to ensure isolation and efficient management of interrupts and exceptions. Memory partitioning utilizes the SAU and implementation IDAU to delineate memory regions as secure, non-secure, or non-secure callable, NSC. This precise attribution helps prevent data leaks and ensures that sensitive information is accessed only within the secure world. Secure peripheral management. The slave access filter is a crucial feature here, controlling which peripherals can be accessed by secure operations, thus adding another layer of security. Secure DMA channel control. Trust Zone lets you set DMA channels to be accessed only by secure operations, or by both secure and non-secure operations. This helps stop unauthorized data transfers and keeps the system safe. Okay, let's move into the security scheme part. The security scheme is a comprehensive plan designed using the previously mentioned security IP and software strategies, covering aspects like secure boot, image encryption, and secure debug. Let's introduce them one by one. Secure boot is a critical security feature that ensures a device only boots using software verified by a trusted authority. It employs a secure boot chain to authenticate each step with methods like ECDSA or RSA. Taking the flash layout and secure boot chain picture as an example, during ROM secure boot, the system first verifies the two flash boot patches and then selects the valid bank to execute. If both banks are valid, the system executes the one with the higher version number. The boot patch then sequentially verifies the non-secure and secure banks. The flash dual bank system enables secure updates, while the image anti-rollback feature prevents reversion to older, potentially insecure software versions. Together, these features maintain the integrity and security of the boot process. This picture illustrates the secure boot authentication flow for a single image. Four groups are involved: the customer, who is responsible for signing the image, the SoC vendor and device manufacturer, who handle the programming of security-related keys, and the image, the end user, who will run the IC. For instance, the public key and its signature are stored in the flash memory with the image, while the hash of the public key is programmed into the OTP to ensure the public key on the flash remains unchanged. The end user will run the IC, during which the secure boot process first computes the hash, validates the public key, and then verifies the signature. Note that image encryption is optional for secure boot, and we will discuss it later. Image encryption involves transforming image data into an unreadable format, only accessible with a decryption key, thereby ensuring that unauthorized users cannot access the original image content. There are two common image decryption techniques: flash on-the-fly decryption, which we mentioned in the security IP section, and RAM copy-based decryption. In the RAM copy-based decryption method, during secure boot, the image is decrypted from flash to RAM, and the CPU fetches instructions from the RAM. The flash on-the-fly decryption method provides more comprehensive security features compared to RAM copy-based decryption. For example, it is not limited by RAM size and reduces the risk of exposing plaintext. In the traditional model, debug interfaces are active during development. However, once mass production begins, they are disabled to protect the security of the product. Now, let's look at secure debug. This strategy allows SoCs to be debugged even after they've been returned to the factory following mass production. This approach not only facilitates problem solving but also prevents unauthorized access to the SoC's internal states and data, ensuring security throughout the product's lifecycle. As illustrated in the diagram, the debug interface is locked during mass production. If debugging is needed, a password must be entered using the MP tool. The chip will then reset and perform a secure boot flow, which checks if the input password matches the one stored in the OTP. The debug interface is reopened only when the password match. Additionally, the try-counter protection mechanism limits the number of invalid password attempts, enhancing security against unauthorized access attempts. Let's continue with our discussion and focus on ARM PSA, which stands for Platform Security Architecture. It's a crucial framework that's designed to enhance security within embedded systems. So, what exactly is ARM PSA? Essentially, it's a strategic approach meant for designing devices that are secure and trustworthy. This framework provides critical guidelines and principles for integrating security comprehensively into the device design process. ARM PSA offers different certification levels to meet various security needs. Level 1. Baseline security. This level focuses on setting up basic security measures that can defend against common threats. Level 2. Enhanced protection. Here, the focus is on shielding the root of trust assets from scalable remote software attacks. This level offers higher security for critical components, protecting them against larger-scale threats. Level 3. Comprehensive defense. This is the highest level of security, safeguarding the root of trust assets from significant hardware and software attacks. It's designed to address the sophisticated and complex threats we face today. Realtek's RTL87X2G series SoC has achieved PSA Level 2 certification in 2024. The security functions included in PSA Certified Level 2 cover 9 crucial aspects to ensure robust protection. These aspects are initialization, which sets up the initial secure state, software isolation, ensuring that different software components are separated to prevent interference, secure storage, which protects sensitive data, firmware update, allowing secure updates to the device's firmware, secure state, ensuring the system remains in a secure condition, cryptography, which involves the use of encryption for data security, attestation, providing a way to verify the device's integrity, audit, which involves logging security events for review, and debug, which requires secure debugging capabilities to prevent unauthorized access during troubleshooting. For reference and implementation, ARM provides trusted firmware, which serves as a solid foundation for developing and managing these security functions efficiently. PKI stands for Public Key Infrastructure. It's a system of roles, policies, and procedures that helps manage digital certificates and encrypt communications. Essentially, it ensures that digital interactions are secure and trustworthy. Within the Matter ecosystem, there's a Matter certificate policy. This policy outlines how the Matter PKI Policy Authority governs security operations. It sets the rules to ensure devices using Matter are secure. Matter PKI has key components for device security. Certificate authorities. The Product Attestation Authority, PAA, ensures top-level security trust. The Product Attestation Intermediate, PAI, connects operational needs with security rules. Device Attestation Certificate, DAC. This certificate checks if a device is authentic and secure. PKI is crucial for securing devices and communications. It assures that devices meet security standards, preventing unauthorized access and enhancing trust in digital interactions. Realtek offers two Matter PKI management solutions. One is managed using AWS Certificate Authority. The other is based on STEC's certificate authority and is still under development. In the AWS-based solution, different customers share the same vendor ID assigned to Realtek, while each customer can use different product IDs to create device attestation certificates. On the other hand, in this STEC-based solution, each customer can use their own product attestation intermediate (PAI) certificates and generate authentication certificates using their own vendor ID. The Device Attestation Certificate Management System provides comprehensive management capabilities for device attestation certificates, ensuring the security and reliability of identity verification for smart devices. This diagram illustrates the certificate management process, from certificate request to secure deployment, involving several key roles. The process begins with the Root Certificate Authority, Root CA, the topmost trusted entity in a public key infrastructure. The Root CA signs the certificate of the Intermediate Certificate Authority, Intermediate CA, enabling it to issue certificates to end entities. The Intermediate CA plays a critical role in the certificate issuance process. It receives certificate requests, which are initially generated by the devices. These certificate requests are sent to a Certificate Lifecycle Management (CLM) system. The CLM forwards the request to the Intermediate CA, which validates and issues the certificate. This issued certificate is then securely written back to the IC, following the original request path, ensuring the authenticity and integrity of the deployment process. On the production floor, numerous workstations are involved. Each workstation is interconnected with the CLM system to maintain unified and efficient control over the entire certificate management process, thereby guaranteeing that all devices adhere to the high security standards required by protocols such as the Matter standard. Additionally, to enhance security and efficiency in key management, the system may employ a key management system, KMS, and hardware security modules, HSMs. The KMS ensures the secure generation and management of cryptographic keys in a controlled environment, while HSMs provide hardware-level key storage and cryptographic computation support, preventing unauthorized access and attacks. Now, let's discuss how to enhance BLE security using certificate-based authentication. First, let's understand BLE pairing mechanisms. BLE uses pairing mechanisms to establish secure connections between devices, enabling peer entity authentication and data encryption. However, traditional pairing methods each have their limitations. Just work, simple operation, but vulnerable to attacks due to the lack of user interaction. Numerical comparison or passkey entry. This method improves security by requiring user input or comparison of numbers. However, it relies on the device's input-output capabilities. Out-of-band (OOB) pairing utilizes external channels such as NFC or QR codes to exchange pairing information, enhancing security but requiring additional hardware or user actions. For devices lacking input-output or out-of-band capabilities, achieving secure pairing can be challenging. Additionally, users often need to participate in the pairing process, which is inconvenient and prone to errors. Certificate-based authentication and pairing can address these challenges. The process is as follows. Both the BLE central and peripheral devices come with pre-installed certificates. During authentication, the devices exchange and verify their certificates. Once verified, they send signed OOB data over the Bluetooth channel for further validation. After that, the BLE pairing process resumes, and a secure connection is established. Next, let's look at the advantages of using certificate-based authentication for BLE pairing. Higher security level. Certificate-based authentication offers a higher security level for pairing, especially for devices without input-output or out-of-band media, by using certificates for authentication. This significantly reduces the risk of man-in-the-middle attacks and other security vulnerabilities associated with simpler pairing methods. Increased deployment efficiency. This approach allows devices to automatically and seamlessly pair and authenticate without manual intervention. It provides strong support for scalability and improves user experience, particularly when managing a large number of IoT devices. Finally, we will discuss the emerging trends in security technology. First, it is essential to understand why robust security measures are crucial in the current technological environment, especially in industrial and safety-critical areas. In industrial applications, we need strong authentication to ensure the system's recovery capability and operational safety. In AI-driven edge systems, we rely on robust roots of trust embedded within infrastructure chips to safeguard critical assets. Next, let's look at PSA Certified Level 4 ISE or SA. It establishes a new standard for chip security, which is particularly important in the AI era. It raises the security bar, ensuring that SoCs can securely manage complex AI operations and adapt to the evolving challenges of cybersecurity. It is worth mentioning that Realtek is developing a secure enclave called RealSecurity. It consists of a security processor and various cryptographic accelerators, providing root of trust, key management, and security functions to Realtek SoCs. Using this secure enclave can further enhance the system's security and quickly adapt to different SoC families, offering consistent security services. Today, we explored security features, aiming to enhance your understanding of Realtek BLE SoCs. If you have any questions, please feel free to contact us through the Real MCU website. Thank you for listening.